Welcome to your Test 3A review over the first three sections of Chapter 3. Here's how this review is going to work. I'm going to go through the 9 practice problems that you will get, and I'm only going to stay on the problems. There's about 1 to 2 per slide on here, and I'm only going to stay on that for just a couple seconds, so I recommend that you pause the video while I'm showing the problem and get it all written down. Then pause the video, work through those 9 practice problems. Then after that, I have it broken up by chapters using that feature on YouTube, and you can go straight to the solutions of those problems and just check the solutions. If you didn't get a certain problem right, then you should fast forward to or go to the part of the video that shows that specific explanation. So basically, this really helps you hone in on what you know, what you don't know, and thus what you need to keep working on. If you really don't understand a certain topic, see what section it's from, take a look back at that assignment, and see what recommended practice problems I have. Go to the online PDF that's provided for you and do those practice problems. And or you can come to my office hours this next week before you take your test on Thursday. All right, so let's get started. Problem number 1. Problem number 2, problem number 3, problems 4 and 5 have the same set of directions. Problem number 6, problem number 7, Problem 8 is not something I'm going to explicitly go over. And then lastly, problem number 9. I recommend here you made sure you had all 9 written down. Go ahead and work on them before taking a look at the solutions and, if needed, the explanations. Best of luck. Here are the solutions to the first 3 problems. Please note that in Part D, your sketch, all it needs to have that is similar to mine is the 3 zeros, as well as the shape of the graph at each one of the zeros because of its multiplicity. How high up or how down low your graph goes is kind of up to you. It might look a little different here and here, but so long as you have the general shape, then you're okay. Here are the solutions to the remaining problems. Again, I said I'm not going to explicitly go over problem number 8. The intermediate value theorem is something that you should be familiar with, as well as have an example written down in your notes for reference. This first problem shouldn't be too bad. Our polynomial is written out in standard form, and we need to find the degree. In this case, the degree is the highest exponent. That is why the degree is 5. It is a quintic polynomial. And the leading coefficient is actually 1 because it's 1x to the 5th. Our constant is our last guy there with no x. If you don't have that, the constant would be 0, but we do have a constant. In this case, it is 12. The number of terms, we want to count how many terms we have. We see we have 1, 2, 3, 4, 5 terms. The number of terms does not have to be the same as the degree, it just happens to be that way here. And our end behavior is probably the trickiest part of this problem. We set up our right end behavior by saying as x approaches infinity, what does our function do or our graph do? And then our left end behavior as x approaches negative infinity, what does our graph of our function do there? And so in order to find the right end behavior, recall that we need to look at the leading coefficient. If the leading coefficient is positive, then your right end behavior is positive infinity. And if your leading coefficient's negative, then your right end behavior is negative infinity. Our lead coefficient is positive, so that is our right end behavior. Then for the left end behavior, we take a look at the degree. If the degree is even, both of our end behaviors are the same. And if our degree is odd, like in our case here, our end behaviors are opposite of each other. In number 2, the polynomial is in factored form, and there are actually 3 factors. The first factor is negative x, the second factor is x plus 2, then it's cubed, and the third factor is x minus 5, and then it's squared. and this negative 1x out front is to the first power. So in order to find the degree, we have to add the exponents together. And the reason that we add the exponents together here is because if we were to multiply this all out, cube this, square this, multiply, then distribute the negative x all the way through, we would have a leading term with an exponent that is the sum of all the exponents that we see now, because this would give us an x cubed, this would give us an x squared, and this a negative x to the first. And so if we multiplied all those out, we add our exponents. So it's 1 plus 3 plus 2. And so that is why this is a degree 6 polynomial. Then the zeros and their multiplicities. The first 0 is 0, because we have negative 1x out here, and what could we plug in there to make it equal to 0? 0. That's one that students most often forget. So our first 0 is, I didn't mean to actually write out the word 0. We'll just write x equals 0, and it's raised to the first power, so it occurs once. It has a multiplicity of 1. Our second 0 is x equals negative 2, and that has a multiplicity of 3. We pick negative 2 because it makes this factor equal to 0. And then the last 0 is x equals 5, and that has a multiplicity of 2. Multiplicity is how many times the 0 or the root, same thing, occurs, and we see that by how many times that factor occurs, which is in the exponent. The next thing we want to do is create a sign chart. This is something that I feel like you guys struggled with the most. So to create a sign chart, it looks like a number line. And in the, almost at the denominator, but underneath, I guess it's kind of a denominator, we want to put the x coordinates, and then so we care about the zeros. So I'm going to go in order, just like a number line. And I only care about those 3 values because those are our 3 zeros. And in like the numerator up above, those are the f of x values. And we know that if we plugged in negative 2, 0, or 5, f of x would equal 0 because they are zeros by definition. Their output is 0. They're on the x-axis. And what we care about is the sign, positive or negative, in each one of these 4 intervals that we have created. And so what we're going to do is we're going to plug a number that is less than 2 in, then a number in between negative 2 and 0, like negative 1, then a number in between 0 and 5, like 1, 2, 3, or 4, and then a number greater than 5, like 10 or 1,000, whatever. We're going to plug that in here to f of x and see if we get a positive or negative output. We don't care about the exact number, we just care if it's positive or negative. So a couple things to look at. No matter what number we plug into this part of f of x, it's always positive because it's squared. So that's just something that we can think before we even start plugging in. All right, the first number I'm going to test out is negative 10, just because it's like pretty far to the left over here. So I'm going to plug in negative 10 into our function. When we plug in negative 10 here, let me rewrite the function real quick. If we were to plug in negative 10, this first factor here would be negative 1 times negative 10. That would give us a positive output. Then this factor right here, if we plugged in negative 10, we'd have a negative number in here, and then it'd be cubed. So that would be a negative output. And then we said that no matter what is in that final parentheses, it's squared, so it's always positive. So if we plugged in negative 10 into our function, we'd have a positive times a negative times a positive, and that gives us a negative output. So no matter what number we plug in to the left of negative 2 into f of x, we get a negative output. Then we'll erase and do it again. This time with a number in between negative 2 and 0. So we're going to plug in, I'm going to plug in negative 1. So if we plug in negative 1, we'll have negative 1 times negative 1, and that's a positive output. Then we'll have negative 1 plus 2 in here, so that's a positive number cubed, so that's positive. And lastly, no matter what's squared is positive, so 3 positives make a positive. Okay, the next thing we're going to plug in is a number in between 0 and 5, and I'm going to choose to plug in the number 3. Okay, if we plug in the number 3 here, we'll have negative 1 times 3, that's a negative. If we plug in a 3 into the next parentheses, that's a positive number cubed, and again positive. So negative times positive is a negative, And lastly, I'm going to plug in positive 10 because that's a number that is greater than 5. It's in this last interval over here. So if we plug in 10, this first one will give us a negative, this will give us a positive, and this one will give us a positive. So we'll have a negative here. Okay, we're going to use all this information to sketch our sign, or we just did the sign chart, to sketch the graph of f of x. And we definitely want to include our zeros and their multiplicities. I don't really care about much else, but here's what I do know. I know that we hit the x-axis when x is -2, when x is 0, and when x is 5. And let's label our axes here. Then we know that to the left of -2, f of x is negative, so it exists down here. And then at -2, we have a multiplicity of 3, which means we cross straight through the x-axis because it's in, well, not straight through, but we do cross the x-axis, and it's like a squiggle because it's a multiplicity of 3. When it's an odd multiplicity, you cross the x-axis, and that makes sense because then after -2, we have to have positive values. So it looks something like this at -2 because of the multiplicity of 3. Then we have to come back down and hit when x is 0. We have to come back down and hit here. And what happens is because it's a multiplicity of 1, it's an odd multiplicity, we cross through the x-axis, we go to the other side of it, and that makes sense too because after 0, we are negative again. Now how high up you go, that is something we don't know. You could plug in extra numbers and kind of see what this looks like here, but this is sufficient. Then we know that we have to come back up and hit at 5, but what happens there is at x equals 5, we have a multiplicity of 2, which means we bounce back and keep going down. And that makes sense here because we're negative on either side of 5, so we don't go above the x-axis again. And it goes back down. So it looks something like this. If you plug this graph into Desmos, you would see something very similar, although most likely is a lot steeper here and probably goes down and up a lot more. We have the general idea using the zeros, their multiplicities, and our sign chart. I talked about this in number 2 if you watch that explanation, but if we have an even multiplicity like 2 or 4, etc., we haven't really seen any greater than 2, honestly. What our graph looks like is it bounces back. So our graph looks something like this. It'll bounce back from the x-axis at that 0, or it'll bounce back, and stay negative. Basically, when a 0 has an even multiplicity, our graph hits the x-axis, but then it does not cross it. It bounces back. So it bounces back. And then if we have an odd multiplicity, like 1 or 3, or 5 or 7, but we really have only dealt with 1 and 3. Those are the most common. I'm going to do one of each. So a multiplicity of 1 and 3, they're similar in that they cross the x-axis at that 0. But a multiplicity of 1 crosses straight through. So that's a multiplicity of 1. That 0 has a multiplicity of 1. And then a multiplicity of 3 also crosses the x-axis, but it does so in kind of a squiggly way, kind of like this. Looks like a cubic. So an odd multiplicity, they cross the x-axis. Whereas if a 0 has an even multiplicity, it hits the x-axis but bounces back. And lastly, multiplicity is how many times that 0 or root occurs. For number 4, we want to divide our polynomial p of x, which is 4x squared minus 1. We want to divide it by the linear binomial x minus 1/2. And we have to see that when we're dividing by x minus 1/2, we're really testing is 1/2 a 0. So if we're using synthetic division, which I'm only going to do the synthetic from here, you won't be tested on long division. I'm going to put 1/2 in the corner. 1/2 is our c value. And then our polynomial p of x has a quadratic term, skips the linear term, and then has a constant. So we have to fill in that 0 there. So we have 4x squared, 0 x's, and then -1 is our constant. So I'm doing part A right now. I'm dividing using synthetic division. So we bring our 4 down, then we multiply the 4 times the 1/2, and that gives us 2. Then we add these two values together. 0 plus 2 is 2. Then we again multiply. 2 times 1/2 is 1. And then again we add vertically. -1 plus 1 is 0. And that's our remainder. So our final answer here, because we started with a quadratic, when we divided by a linear polynomial here, in this case a binomial, we go from, we drop down one exponent, we drop down 1 degree, basically. So because we started with a quadratic, our quotient here is linear. So our quotient, q of x, is 4x plus 2. Again, started with a quadratic, we divided by a linear, and then it drops down, so this drops down 1 degree or 1 exponent. So it drops from a quadratic polynomial, and then it goes to a linear, in this case binomial. Now we have a remainder of 0. In division in general, if you divide and you get a remainder of 0, that means those numbers fit together real well. And actually, I'm skipping part B real quick. I'm getting ahead of myself for part C and D. Part B, real quick, is asking what is p of 1/2. This is the remainder theorem. The remainder theorem tells us that our remainder is a quick and easy way of plugging in that number into our function. So if we were to plug in p of 1/2, you totally could have done that here and plugged it in. But the remainder theorem tells us that our remainder tells us that real quick and easy. So p of 1/2 is 0, our remainder. All right, and when we have a 0 like that, is x equals 1/2 a 0? So is x equals 1/2 a 0 of our polynomial, which is 4x squared minus 1? Well, yes, it is. Because p of 1/2 is 0, when we divided by its corresponding factor, we got a remainder of 0. That means that 1/2 is a 0 of the polynomial. It would lie on the x-axis, and we know that basically because of part B here. Part D, is x minus 1/2 a factor of p of x? Well, since x equals 1/2 is a 0, x minus 1/2 is definitely a factor. And that's the relationship between zeros and factors, so this goes both ways. If x equals c is a 0 of some polynomial, then x minus c is a factor, and that goes the other way too. If x minus c is a factor, then x equals c is a 0. If we did not get a remainder of 0, then p of 1/2 would not have been 0, and we would say no to both of these answers. Number 5 is similar to number 4, so we're going to start by dividing. Here we want to put -1 in the corner because we're dividing by x plus 1. Basically, we're asking, is -1 a 0 of this polynomial? And we do not skip any terms here. We go from cubic, quadratic, linear, and constant terms. So their coefficients are actually 1, 2, 3, 4. It's kind of fun. With synthetic division, we bring down our first number, which is 1. 1 times -1 is -1. Then we add vertically. 2 and -1 added together is 1. 1 times -1 is -1. Then we add together again. 3 and -1 is 2. 2 times -1 is -2. And we finally add together again to get our remainder, which is 2. All right, because we started with a cubic, we go down by 1 exponent or 1 degree for our quotient. So this is a quadratic answer. So q of x, our quotient, is 1x squared plus 1x plus 2. And our remainder, which we could write as r of x, is 2. So we divided. Part B is asking us about the remainder theorem, which tells us that if we were to plug in -1, we would get whatever the remainder was, which in this case is 2. Could you plug in -1? Sure, it's a lot more work. All right, is x equals -1 a 0 of our polynomial? Well, did we get 0 out? No. If we were to plot this, x equals -1, right? We don't output on the x-axis. The coordinate point is -1, 2. It's not a 0. So x equals -1 is not a 0. We did not get a 0 as our remainder. So no. And part D comes directly from part C. Since x equals -1 is not a 0, x plus 1 is not a factor of p of x. It's not a factor because we had a remainder. It didn't fit in evenly. Number 6 is another division problem. I don't know why I'm writing number 6. All right, we want to divide by x minus 3. That means to do synthetic division, we put a positive 3 in our corner. We do see that we skip the quadratic term, which is why we have to put a 0 placeholder in there. So we have our cubic term, we skip the quadratic term, we have our linear term, and then our constant. The synthetic division process, bring down the first term, then multiply by the number in the corner box, so we'll get 12. Add vertically 0 plus 12, then repeat. 12 times 3, 36, then add vertically to get 38. Again, multiply by 3, so 38 times 3 is 114. And then add vertically, a lot of ones. Our remainder is 111. So we want to write p of x as this final way here. Now recall that what we're dividing by is d of x, our divisor. The original guy is p of x. Q of x is the quotient. So our quotient here, because we started with a cubic, we go down to a quadratic here. So this is 4x squared plus 12x plus 38. This right here is our remainder. And so to rewrite p of x, I'm going to just rewrite p of x out. It's 4x cubed plus 2x minus 3. So I'm going to do this final thing all in blue. And that equals, when we divided it by x minus 3, we got our quotient from synthetic division. So when we multiply these two, what we divided by and what we got, we don't quite get this final thing because we have that remainder at the end, plus 111. So that's what our final answer looks like. And we got this through synthetic division. Here we're given a cubic polynomial, and the first thing we want to do is use Cauchy's bound to find the interval that contains all of our real zeros. And in order to do this, we have to decide what m is. M is going to be the largest of these numbers so we'll have 3 of them, and in all the denominator, it's the absolute value of our leading coefficient. Our leading coefficient here is -2. So we have to choose the biggest number. Then in our numerator, we put the absolute value of our other coefficients slash the constant. So -5, 3, and then 20. Okay, the biggest number, this number is equal to 2.5, 5 halves. This number is equal to 1.5, 3 halves. And this number is equal to 10. So 10 is our winner, m is 10. And that means our interval is -m plus 1 to +m plus 1. So our interval, m plus 1 is 11, so it's -11 to +11. So all of our real zeros are on the x-axis between -11 and +11. All right, for part B, we have to use our rational zeros theorem. And in order to do the rational zeros theorem, we have to list our p's and our q's. And our p-values are all of the factors of the constant. So our constant here is 20. So we want to list all of our factors of 20, and we need to put a plus or minus in front of all of them. The factors of 20 are 1, 2, 4, 5, 10, and 20. I saw some students like to listing them as like 1 and then 20, 2 and then 10. That's great. The things that multiply to give you 20. And then Q is the same idea except with the leading coefficient, in this case with 2, well, -2. But we put a plus or minus to kind of cover it being positive or negative. So those are our factors of 2. So then all of our possible rational zeros are all the p over q values. So when we put all of these p values over 1, we end up just having the p values because putting them over 1 does not change them at all. So I'm just going to relist all of our p values. That's like putting them all over 1. Then the next thing that we want to do is put all of our p-values over 2. So we're going to put 1 over 2. We don't have that yet. That's 1/2. So we're going to put plus or minus 1/2. The next p-value is 2. 2 over 2 is 1. We already listed 1. Don't need to list it again. The next p-value is 4. 4 over 2 is 2. Don't need to list it again. 5. 5 over 2 is 5/2. We don't have that one listed yet, so we'll list it. Then we'll have 10. 10 over 2 is 5. We've already listed that. The last one's 20. 20 over 2 is 10, and we've already listed that. So our possible rational zeros are right here by the rational zeros theorem. The last thing we want to do is use Descartes' rule of signs to find the positive and negative, well, how many positive and negative real roots we can have. So let's first do the positive real roots, how many we can have, by finding p, capital P. And the way that we do that is we count how many sign changes are in f of x. So it's up here. I'm not going to rewrite f of x. We go from negative to negative. That's nothing. Negative to positive, that's one sign change. Positive to positive, that's not. So our capital P is 1. That means we can have 1, or we can go down by a multiple of 2. Well, I can't go down by 2 because I'd have a negative amount. So there's only one positive real root. The next thing that we do is we have to find the number of negative real roots, and we do that by finding f of negative x, which when we do that, the terms that have the odd exponents are going to change signs. So we'll end up having a positive 2x cubed, the minus 5x squared stays the same. Then we'll have a minus 3x and a plus 20. The reason that it's like this is because whether or not we plug in x or negative x, an even exponent is not going to change the outcome. However, plugging in a number versus its opposite, an x versus a negative x, with an odd exponent, it changes the outcome by making it the opposite sign of what it was. This plus 20 here, or any constant, is not affected by what we plug in. So now we want to count the sign changes that we have. We're going from positive to negative, that's 1. Negative to negative is not 1. Negative to positive is another 1. So our capital N is 2. That means our negative real roots are that value. We either have 2 of them or we can go down by 2. So we can have 2 or 0 negative real roots. And that's because the total amount of roots has to be 3 by the fundamental theorem of algebra. One of them is definitely a positive real. So we could have 1 real root, it would be positive, and then 2 imaginary roots. We would have no negative real roots in that scenario. Or all 3 of them could be real, and out of those 3 real roots, 1 would be positive and the other 2 would be negative. For number 9, we can approach this in a lot of different ways. The way I'm going to do this is I'm going to first use the rational zeros theorem to list all of our possible rational roots. And I'm going to recognize here that since our leading coefficient's 1, I'm not even going to list the q values because we're going to end up putting all of those p values over 1 anyway. So by the rational zeros theorem, it's just the factors of 16, plus or minus those. So it's plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 16. Those are, and 8, goodness. Maybe I should list them in a different order. Okay, there we go. So I think that's all. There we go. That's all the factors of 16. And again, they're all over 1. The next thing that you can do is you can see how many of them may be positive versus how many of them may be negative using Descartes' rule of signs. That is completely up to you. I am going to do that real quick. So I'm going to use the rule of signs. So let's see if we should maybe check positive or negatives. Maybe it'll help us. I'm not sure. How many sign changes do we have in f of x? Only one. So that means we definitely have one positive real root. Okay, that's enough for me because I know that we have to have a positive real root. That is definitely going to mean that I'm going to have either 2 or 0 negative real roots, so that's not going to help me that much. So I know one of them has to be positive, and if it's rational and positive, great. So I'm going to check the positive numbers using our synthetic division. First number I'm going to check is 1. 1 is always the easiest number to check. So we have a 1, a 2, a negative 12, and a negative 16. We'll go through this pretty quickly here. I'm not going to explain the synthetic division process at this point. Okay, this is not going to work. We didn't get 0. Okay, so 1 doesn't work. Let's try 2. When we try 2, we'll have 1, 2, negative 12, negative 16 again. Synthetic division's kind of fun if you can do it pretty fast. Nope, not 0. All right, I'm going to try 3. Why am I trying 3? What is going on? I'm going to try 4. 3 is not a possibility. Let's try 4. Maybe this will work. 24. This is not looking like it's going to work. Maybe the positive real root that we're getting is not rational. All right, let's see. I'm going to work these out and we'll see what we get in a second here. All right, I've tried all the positive rational roots, possible positive rational roots, and none of them work. Now, here's the thing. Descartes' rule of signs said we do have one positive real root. That real root is just not a rational number. It's some other number that we'll have to find once we get the quadratic and use the quadratic formula. So, Descartes' rule of signs then, since one of them has to be positive, either 2 of them or none of them are negative. So I need to check the negative roots next. So let's wipe this board clean and try the negative numbers. Okay, let's check -1 and see. So none of the positive numbers work, so I'm going to slice all those positives off. Let's try -1. Again, I'm going to move through these pretty quickly. Nope, doesn't give us 0, so let's try -2. So neither one of those works. We'll try -2. Could I graph this? Yes, that's a great question that nobody asked just now. Oh, not 0. Okay, if this next one doesn't work, then I'm going to graph it and see what the root is. But I'm teaching you persistence, you know? Oh, dun 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 off. -4. Okay, -4 works. Yes. All right, so because -4 is one of our real zeros, we know that the other two are going to be irrational, meaning they're not either -8 or -16. One of them is positive. So we need to take this quadratic here and find the other two. This quadratic is not going to be factorable. So I'll make that real tiny. And then here's our quadratic. We'll do this in navy blue. So here's our quadratic. It is x squared minus 2x minus 4. And I want to set that equal to 0 to solve it. Now we know it's not factorable. There's not two numbers that multiply to -4 that add to -2. Therefore, to solve a quadratic, you can never go wrong using the wonderful quadratic formula. And it's the opposite of b, plus or minus b squared. B squared is always positive. 4ac all over 2 times a, which is just 2. 2 times 1. All right, under the square root, our discriminant will end up being 4 plus 16, so it's 20. Now we can break down the square root of 20 into root 4, root 5, because 4 is the biggest perfect square that is a factor of 20. And root 4 is 2, so we'll cross it out, bring it out as a 2. then we can actually simplify all those 2's and divide them all by 2. So it's a 1, this is a 1, and this is a 1. And the only one we still need to write is the one out in front. We don't need to write a 1 root 5, nor do we need to write all over 1. So our 3 roots are -4, 1 plus root 5, that's our positive one, and 1 minus root 5. That's our other negative one. Phew. Now, if you wanted to check these on Desmos, you could see what 1 plus root 5 is as a decimal, same with 1 minus root 5, and you would see that that's where you're going to hit the x-axis 3 real times.